We have one absence. Who is it? Oh, okay, I got it. Okay, so let me go ahead and start off with College Board updates, which for y'all is two things. Number one, what's the deal with the SAT? And then number two, what's the deal with AP tests? So number one, in terms of the SAT, nobody knows. Last week, there was supposed to be an online seminar. And I'm going to go ahead and say online seminar just because I think the phrase webinar is terrible and cheesy. But last week there was an online seminar to try and talk about, like, hey, the College Board is making these changes and these adaptations and whatever for the upcoming tests. And that online seminar ended up getting canceled because apparently they don't even know what they're doing yet. It's really weird to me that they're totally willing to let people take AP tests from home, but not the SAT. I guess it's probably because that second one, the SAT, is like way more important to them in terms of money. So they're gonna, protect that one a lot more closely. But in terms of like college responses to the fact that they can't administer SATs, a bunch of colleges have said that, like, if you were a senior and you were waiting to take the SAT, if you were a junior and you were waiting to take the SAT, a bunch of colleges are waiving that requirement for this year. Like, just in case you didn't have the SAT already down and you were waiting to take it and apply by the fall, in case they aren't able to give an SAT by the time college applications are due around Thanksgiving, a bunch of schools have waived it, and you don't need it if you don't already have it. If you're prepping for it, you should continue prepping for it in case they are able to administer a regular SAT in time for college applications. But I wouldn't sweat it. And I would look up, if you already have your short list of colleges, I would look up campus by campus to see which campuses have waived the SAT requirement. And actually, since it's fourth quarter and y'all are my juniors in my homeroom, I'll probably make an assignment of making a short list of your colleges in case you haven't already done that mentally. But I'll build that into the lesson plans over the next week. It'll, be fairly easy to obtain credit, yeah. And then on the topic of the AP tests, have y'all seen those updates? Because the AP tests are ready to go from the College Board's perspective. So yeah.
Ms. Robinson,
Mm-hmm.
So you know how they have the lockdown browser and stuff?
Yep.
For on that day, which is going to be, most of us are on the 16th, along with the rest of the U.S.
Mm-hmm.
That browser has the issue of crashing. So let's say hypothetically, for some people it crashes. What would be the protocol? Did they ever go over that or no?
Nope. You just deal with it. You try and make it run again, or you hurriedly go to another device. I would make sure that you have multiple devices that can run it ready to go the day of, just in case. But I do foresee technical difficulties basically no matter what. Even when they get to the upload time, man, I super doubt that their servers are going to be able to handle all of that load. I would just expect technical difficulties on the day of the AP test. I think the only saving grace is that none of you have tests day one, because day one will be the day that they have the worst issues. But luckily day one is Physics C in the morning, which we don't offer. And then in the afternoon, it's AP US Government. So the seniors will get to tell you after they're done with their AP tests on Monday exactly how ugly it was. But yeah, I think technical difficulties are just guaranteed. Anyway, just so y'all know what your AP tests are going to look like in case you haven't heard it yet from your AP teachers or whatever. The tests are going to be 45 minutes each. They're going to be from home. I posted the schedule of AP tests on the class website. It's like the most recent posting that isn't the link to this Zoom meeting. The test will be from May 11th to May 22nd. And all of the tests will now have a similar structure. So for anything that is English or history, it's going to be one longer form essay. And all other tests aside from history and English tests will be 2 questions each. The first question will be 25 minutes. You get a chance to upload that, a 5-minute window. And then after that, the second question is 15 minutes. After you answer the 15-minute question, you get another 5-minute window to upload it. And then after that, it's done. So be aware of that. Also, for every single one of the AP classes, since not all schools are doing online learning or whatever, the College Board on their YouTube channel has a playlist for every single class, a ton of review content. And I'm going to assume that they are giving away a bunch of hints towards what could be asked on the tests. Because what else can you do when you're changing up a test this late in the game? The only bummer about it is that, man, it condenses all of the classes down to 2 questions. So it really does feel like gambling in terms of what I choose to review with the AP Physics group of like, am I going to guess the 2 topics right or wrong, right? Because that'll be highly determinative of the class's score. But yeah, any questions on that stuff? No? Anybody have a good story from spring break they want to share? No, I figured not. I skinned my shins like a middle schooler, man. Like my whole right shin is just raspberry jelly from like knee to ankle. Because I went running the first day of spring break and I've been running at night to like avoid the crowds out there. And I had a spider like drop down in front of me. And I jumped a cement barricade like while running to avoid touching a spider. And I ended up scraping my whole shin. It's a very, very like middle schooler type injury of like all, you know what I'm talking about? Like how middle schoolers always have scraped up knees. Motor skills are hard, dude. Motor skills are rough. Anyway, let's go ahead and go over the system of linear equations, and then we'll get going with talk of the mid-chapter quiz, and then we'll see how far we get through notes today. Did anybody out there get just like a straightforward answer? What was the ordered pair where these 2 guys cross?
Is it 1 and 0?
I believe it is 1, 0, but let's go ahead and show that. So do y'all want to do substitution or elimination on this Tuesday morning?
Elimination.
Yeah, and that's actually wiser considering what we're going to be doing for the second half of this chapter. Well, let's go ahead and take this and eliminate it across x. And to do that, we're going to multiply this second line here by -4. So if I take the second line, multiply it by -4, this is going to give us a set of 2 equations. 4x plus 3y is equal to 7, and -4x plus 8y is equal to 4. And then the point of that is so that the x's both have the same value but opposite signs. So now I can take these 2 linear equations and I can add them together. And the point of this step of making them equal is so that when I add them together, 4x plus -4x is 0x, plus 11y is equal to 11. So 0 times anything is 0, 11y is equal to 11. This means that y is equal to 1. That's the first part of our answer. And then how do we get back the second part of our answer?
Plug it into one of the
Yeah, all we have to do is take it and plug it back in. And I'm actually going to plug it into this second equation because x is already solved for, or x is already, I should say, unitary. X minus 2y is equal to -1. X minus 2 times 1 is equal to -1. So I'll take and I'll add 2 to both sides. 2 plus -1 is?
1.
So our ordered pair here is going to be 1, 1. Are there any questions there on the warm-up that the answer to this problem is 1, 1?
No, looks good.
Okay. Then let's go ahead and start off by going over the mid-chapter quiz. If y'all want to pull that up, the document, we can go ahead and talk about it, and I'll answer any questions about it now. Though class scores were pretty good, even though taking a midterm from home is weird. It sucks, but like providing feedback on that stuff is really difficult. So in case you want to know a breakdown of precisely where you lost points, you'd have to email me directly and then I'll type it up for you. Just because I don't want to do that for everybody. Like if you got an A and you're happy, cool. But yeah, if you want a breakdown of exactly which questions you lost points on, shoot me a direct email. Because the way that I was grading it is basically I have the answer key in one hand, and then I have a roster of your guys' names in the other hand, and I go along and I keep track of the points for each question. But like also doubling and making all those comments on Google Classroom feels like overkill, considering I'm sure everybody who got like a 95 or higher won't even check the feedback. So like I said, if you want to know exactly where you lost the questions, shoot me an email and I will respond with a quick breakdown of what points you got on which questions. Just so y'all know, on the mid-chapter quiz itself, questions 1 through 3 are each worth 3 points. And then all the rest of the questions are worth 4 points each. And then the bonus question at the end is worth an additional 3 points. So on this particular quiz, 41 points were available, but if you got full credit on the extra credit, one could have scored 44 out of 41 points. Are there any questions to about the quiz? I can just give you the answers if you want to know, or I can work them out real quick. Or like it's been so long and nobody's thought about the quiz since you turned it in, so nobody has any questions. If you do, yes.
Yeah, can we actually do number 11?
Oh, sure, yeah. And actually, I won't do all of number 11, but I can definitely
just start off and
yeah, the setup is the important part. So from the mid-chapter quiz, question number 11, we wanted to use partial fraction decomposition in order to rewrite x plus 1 divided by x cubed plus x. So the first thing that we want to do is we want to factor this denominator. I'm sorry, x cubed plus x, not plus 3. Yeah. Anyway, the first thing we want to do is we want to factor out this denominator. So this is actually equal to x plus 1 divided by x times x squared plus 1. Both of those have an x in them, so we can factor that out. And then from here, there's nothing else we can do. Now, if this was x squared minus 1, then this would be something that we could factor into simpler terms. But with this term being in the denominator, here's our partial fraction breakdown. I could have a divided by just x. That's part 1. And then my other denominator is x squared plus 1. And since this is quadratic, our numerator needs to be 1 degree lower, which means it needs to be linear. So our numerator is going to be bx plus c. And then from here, we can multiply out the denominator and solve for a, b, c. If you do this, you'll find that a is equal to 1, b is equal to -1, and c is equal to 1 also.
All right, thank you.
Yeah. Okay, so if there are no other questions, let's go ahead and get into notes. Today we'll be talking about 9.4. Our basic introduction to matrices, though y'all have mentioned that this is something that you've done before. So most of this section will be a review. The new stuff about matrices will most likely come in the next section in 9.5. Today we'll be talking about in the next section 9.6. Today we're talking about section 9.5. Matrices which is just the pluralization of the word matrix. It's one of those words like wolf or mouse that has its own special pluralization because of the language that it comes from. Matrices and matrix operations, which, you know, as a physicist, as somebody who studies physics, boy, are matrices everywhere. They're everywhere in mechanics, and they're also a huge topic in engineering and computer science, mostly because they are a shorthand to writing extremely complicated systems. So in a lot of uses where you see them, they are being used as a way of writing down a large amount of information in the smallest space possible by taking advantage of the positions within the matrix. And the other nice feature that they have is that almost as a consequence of using that formalism, there are extra emergent things that we can learn about those systems. We'll be talking about that more in the next section when we talk about determinants. So let's just go ahead and start off with basic definitions. Yeah. So, yes?
Mark just told me that he lost internet connection.
Okay.
He's gonna try to join back.
Okay. A matrix is an array of values and or variables laid out rectangularly. That is to say that a matrix is just going to be a rectangle of values, and the size of the rectangle could be basically of any dimension as long as those dimensions are 1 or higher. So we typically say that a matrix has dimension of m by n, where m and n just represent the number of rows and columns. Yeah, I'm sorry. Yeah, where m is the number of rows and n is the number of columns. So a regular number itself can actually be thought of as a matrix. So a singular value, if I just had the number 4, we could say that this number 4, right, this regular old counting number, this integer, can be thought of as a 1 by 1 matrix. We could also have a square matrix, some kind of 2 by 2, where on the inside of the matrix, I had both numbers and variables. So I could have 3, 7, B, 42. Or we're capable of having a matrix of any dimension, again, as long as these dimensions are greater than 1 each. I could have some 2 by 4 of 1, 0, 0, 1, 0, 1, 1, 2, etc. As long as it is rectangular, it is some kind of matrix. Now, within any given matrix, all of these entries can be named, and it's going to be based on their row and column position. So within any single matrix, let's say just for example that I have a 3 by 3, right? So I have a 3 by 3 matrix A. I can say that within A, right, we're going to have 9 entries in here. that every single one of these entries can be thought of as being A, so long as we properly name that position of A within the matrix. So let me tell y'all, or to show you the like basic numbering or naming scheme, whatever way you want to think about it. We would say that this first one right here would be A11, because it is the value of matrix A, which is in row 1 and column 1. So then this would be 1, 2, row 1, column 2, 1, 3, row 1, column 3. So this next one here would be 2, 1, row 2, column 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Where again, that first number is the row, the second number is the column. And again, this is a unique thing just because of all of the things that tend to be emergent from writing a matrix out in this way. One easy one is that in a lot of cases or applications, we'll be interested in the diagonal of a matrix, right? Where the diagonal of a matrix, and I'm not going to define this in any, I'm not going to define this in any formal way just because we're not doing anything with it yet. But let's say that the diagonal of a matrix is yellow. It's literally the diagonal elements along the matrix, right? From corner to corner, and just out of tradition, we do top left to bottom right. What's a way that we could call out the diagonal of the matrix with values? What special rule do you see the diagonal values of the matrix having here?
There are multiples of 11, I guess.
So don't think of it that way. These are not multiples of 11. It's not that this is 11, this is 1, 1, right? This is row and column.
Oh, I see. Okay.
But no, you have the right idea. So yeah, the thing that makes it look like these are multiples of 11 is the fact that the value in both positions is the same. So another way of talking about the diagonal of a matrix is to say that it is A sub n m. And let's go ahead and think back to our logical rules from geometry for a second. What was this shorthand for?
Such that?
Such that n is equal to m. So if you are interested in the diagonals of a matrix, right, and you want to try and describe a rule that will tell you, well, what exactly is the diagonal of a matrix? It is the values whose row is equal to their column. If you are in row 1 and column 1, you're on the diagonal. If you're in row 2 and column 2, you're on the diagonal. If you're in row 3 and column 3, you're on the diagonal. Any other value where the numbers are different, those are off of the diagonal. And I know this seems like overkill, especially because the matrix that we're talking about in this little example here is a 3 by 3. But matrices can be any dimension. You could have a 10,000 by 10,000 value matrix. And if you have 10,000 elements on your diagonal, this could be a convenient rule for locating them. So let's talk about some of the things that our matrices can be used to model before we talk about what the rules and the operations are, right? So why is it that we care about this? What can be done with matrices is innumerable, mostly because all of the things that your computers do, like even the act of sending a text message in itself is a type of matrix operation, because that text that you type in, it is transformed into a matrix. That matrix is sent to your local cell phone tower. That cell phone tower relays it to your homie's local cell phone tower, where that text message is received by their phone as a matrix, and then the inverse operation is done on that matrix to take it and turn it back into the text message that was originally sent. However, that's all very heady. That's like way past, those are college applications of what we can do with matrices. Here are some simple examples of where we'll be using this. In the warm-up, we had that system of linear equations. 4x plus 3y is equal to 7. And x minus 2y is equal to -1. Well, this system of linear equations can be turned into what we are going to refer to as an augmented matrix. And again, exactly how it is that I am doing this isn't super important right now. This is what we'll be coming back to next section. Again, I just want to give some like cases of where this might be useful. If we were to take this system of linear equations and rewrite it as an augmented matrix, here's what it would look like. 4, 3, 1, -2, and 7, -1. So what is it that I just did there?
You just took the values and put it in a matrix, I guess.
Exactly. So instead of writing this equation with the x's and the y's, because as long as we kind of like agree on having this standard, that, oh, when I write a linear equation in standard form, I'm putting the x piece first, I'm putting the y piece second, and then the constant goes on the right. Well, if we can all agree on that rule set and agree to do it that way every time, then as long as I know that column 1 means x and column 2 means y, and this thing that I'm putting off to the right-hand side, these are our constants. As long as we can agree on this convention, then I don't have to write the x's and I don't have to write the y's and I don't have to write the equals. And solving this will give us the exact same answer as solving this, except we'll be able to achieve it with a lot less writing. So one use of using these augmented matrices is to solve systems of equations. And here's another thing that is commonly used, which is commonly, a thing which matrices are commonly used for is also vectors. So we had a little bit of talk about vectors, but all that you need to know about a vector is that a vector has a magnitude and a direction. It is a mathematical quantity which has nothing else about it. So I could draw some vector like this, and I could tell you that this vector has a length of 3 in the x direction and a length of 4 in the y direction. And if that was the case, then there's a bunch of stuff that we could characterize about this vector, right? That I have some sort of arrow, it could represent a force or a length or tension, whatever vectorial term you want to think about, right? And how long is this vector if it's 3 in the x direction and 4 in the y direction?
5. 5.
Yeah, so the absolute value of this vector here would be 5 in this total length, yeah? And then we would also have some angle theta that it is oriented at, and which trig function would we use to solve for theta?
That doesn't matter
Inverse sine.
because we have all the values for the sides.
You are correct, yeah. So since we have the hypotenuse, we could use any trig function for it. Traditionally, we're going to use tangent just in case it's not a perfect Pythagorean triple and the hypotenuse doesn't work out to be an integer.
All right, yeah.
So we would say that this is 5 in length and theta is equal to inverse tangent of 4/3, tangent, opposite over adjacent, etc. Or if we agree that this is vector B, I could represent this idea of vector B simply as a matrix just by saying that, hey, B is the vector whose components are 4 and 3. B is the vector whose components are 4 in the, oh, I'm sorry, I got that backwards. B is the vector whose components are 3 in the x direction and 4, oh no, did my whiteout break? I think my whiteout broke. I guess I'll just have to stop making mistakes. B is the vector whose length is 3 in the x direction and 4 in the y direction. And this representation of vector B captures all of the same information as this representation. Yeah. Anyway, when it comes to adding matrices, we're not really going to get into the operations that make matrices special in this section. That'll be something that we do next section. Let's go ahead and talk about some of the rules of dealing with matrix combinations. Okay. So here are the rules for doing operations with multiple matrices. So first off, let's go ahead and talk about addition and subtraction. So addition and subtraction are the same operation, right? One is just the negativized version of the other. That is to say that 2 minus 1 is actually 2 plus -1, and there is no difference in how those things are executed or what the outcome is in the end, right? So the same is true for matrices. These two things are actually the same, so all the notes that I'm about to write apply equally to both. However, we have a couple rules. So for two matrices to be added or subtracted, they must have identical dimension. They have to be the exact same size. So if you were ever asked to add or subtract two matrices that have different sizes, it is some sort of trick question or concept question. You can't actually do that. It's a nonsense request. And when you take and you add or subtract two matrices, all that you're actually going to do is add or subtract corresponding entries one by one. Huh, that's weird. My webcam's contrast got all dark, right?
Yeah, I was just about to.
There's a right way I can fix it. There's a wrong way. Let me try and fix it the wrong way first. Okay, that's fine. So here's what I mean by this and why we like that nomenclature where we can refer to the entries of a matrix one by one. This is to say that to take matrix A and add it with matrix B, this is the same as, that is to say, it is to go to every single element within A, element 1, 1, and add it to element 2, 2. I'm sorry, to take element 1, 1 from A and add it to element 1, 1 from B. So we're going to go across A to every single entry, that is N and M, and we're going to go through B and add it to every single element, that is N and M. And of course, we'll do an example at the top of the next page. So, 2 quick examples. Okay, item number 1, take this matrix, add it to this matrix. Operation, or example 2, take this matrix, add it to that matrix. So what do we do here for item number 1? What is the sum of those two matrices?
Not possible. They're not the same size.
Yeah, no sum. Yeah, it's just a nonsense question. It's not really a thing that we can do. And then item number 2, this is a thing that we can do. And so we're going to take these two matrices and we're going to add them one by one across all of the elements which correspond. So if this is matrix A, then I could say that A11, well, that's 4. And if this is matrix 2, well, this is, I'm sorry, if this is matrix B, this is B11, right? And so to get the new matrix element 1, 1, I'm going to take A11 and add it to B11, which will give me A plus B 1, 1. And that is the most complicated way to think about it, which is why I'm not like writing it down as I go along. But yeah, to add two matrices is literally to just add the corresponding values, the elements which line up. So this top right one is going to be 2 plus 7, 2 and 7, 1 and 0, 1 and 0, and then 3 and negative 3. And so the final output of this matrix addition is going to be 10, 9, 1, 0. Is that okay?
Yeah.
Okay. And now a couple rules about this stuff, and what I'm about to write down is really, really, really important because this is vocab you were taught in elementary school, except you're not normally asked to use it anywhere in an interesting way, not until matrices. The following properties are crucial when it comes to matrices. When it comes to matrix addition and subtraction are both associative. This is, I'm sorry. You know what, I guess that's fine. Matrix addition and subtraction are both associative. This is to say that if you are going to add several matrices together, the order in which you add them or subtract them is utterly irrelevant. This is to say that if I'm taking matrix A plus matrix B, and I'm also adding to that matrix C, this is going to give me the same result if I were to add them in some other order. And here's typically how we represent this. A plus B first, then plus C, will give us the exact same result as A plus B plus C, even if we add B plus C first. So addition and subtraction are associative, and this is true of regular numbers, right? 1 plus 2 plus 3 is 3 plus 3, which is 6. 1 plus 2 plus 3 is 1 plus 5, which is still 6. So something being associative isn't interesting, but we're going to see as we move along cases where matrix operations are not associative. That is to say, the order in which we do them, the way that we group them, causes us to get a different result. Matrix addition and subtraction is also commutative. And again, this is boring. This is to say A plus B is equal to B plus A. But the reason why we're talking about this now is that while addition and subtraction are commutative, right, the order in which we write the characters is irrelevant, we are very quickly going to find ourselves in a place where the operation is not commutative. That is to say, A combined with B can give us something different than B combined with A. Are there any questions here up through addition and subtraction? Basic stuff, right?
Yeah.
Okay. So now let's go ahead and move on to scalar multiplication. When it comes to scalar multiplication, scalar means that we are simply going to change the size, but not any other feature of that matrix, right? So when it comes to scalar multiplication, this is to say I'm literally going to take just a number and multiply that by our matrix. And this has some pretty straightforward definitions. So if I were to take some constant c and multiply this into my matrix A, where A could be, you know, any dimensionality, all that we're actually going to do is we're going to take that scalar and we're going to multiply it equally into every single element within the matrix. So where A was originally, you know, some set of numbers, A11, A12, A13, etc., all that this is asking us to do is to take those elements, and to each one of those elements, they all get multiplied equally by C. So if this was our original matrix, to hit it with the constant C is to hit every number inside with C. One interesting thing, because I mentioned it at the top in terms of applications, if our matrix is meant to represent a vector, and this is not regular stuff, this is a side note, this doesn't change the direction of a vector, this only changes the length. So I mentioned at the top that we had that vector 3, 4, right? So I could say that I have some vector b equal to 3, 4. Let's say that I take this and I hit it with 2. What would 2b be equal to?
6, 8.
Yep. This new vector points the exact same way as the old vector. This is to say that they are parallel. So if this is 3, 4, if this is b, 2b is in the exact same direction. It does not rotate it, but it does make it twice as long. It is just taking our vector and it is rescaling it, but it is not turning it. If you want to take a vector that is represented by a matrix and turn it, you'd have to change x and y by different amounts. Some additional things about scalar multiplication. Scalar multiplication. And again, we're going to talk about a couple mathematical properties with vocab here, because what's interesting is what's going to be in tomorrow's notes, the places where this breaks down. Scalar multiplication is distributive. Ooh, I shouldn't have put colons there. This is to say that if I was going to take a scalar and multiply it by the sum of two matrices, that I can take that constant and I can distribute it to both terms, and that CA plus CB would give me the exact same result. Anyway, I'm going to stop lecture here and we'll pick up tomorrow with matrix multiplication. I'm going to take the homework and I'm going to post the whole thing today, but you'll only be able to do the first half. And then we'll go over the second half tomorrow. Tomorrow we'll talk about matrix multiplication, which I always hold off for a second discussion just because it's way more complicated than these first two things. And that is where distributivity, associativity, and commutativity fall apart. I'll see y'all then tomorrow morning at 8:15. Y'all have a nice day. Welcome back.
See you, Mr. Robinson.
Thank you, Mr. Rob.
Yep. Bye, everybody.